Hello, everybody. My name is Ashwin Menon, and today I'm going to be discussing research on the laser shock peening of nickel-titanium alloys. Nickel-titanium, also called nitinol, is a type of shape memory alloy. Shape memory alloys are a type of metal that have a unique property in which they can be deformed and then reformed to their original conformation with the application of heat. Nickel-titanium's shape memory alloy property, along with its biocompatibility, makes it highly useful in creating a variety of biomedical devices, whether it be stents, braces, or implants. However, these biomedical devices are limited due to nitinol's fatigue, metal fatigue, due to its shape memory alloy property. And therefore, improving the fatigue resistance of nitinol is important in widening the applications of nitinol's medical implants. One way to do so is using laser shock peening. Laser shock peening is just a machining process in which a laser beam is directed to the surface of a workpiece, in this case, nitinol. The impact of the laser beam creates a compressive force that travels through the workpiece, strengthening its core. Additionally, a plasma plume is produced at the surface of the impact of the laser beam. This plasma plume has increased heat and pressure, which machines the surface of the sample, improving its fatigue resistance. Our research implements a magnetic field in LSP. This magnetic field confines a created plasma plume. Confining the plasma plume increases the temperature and the pressure of it, and therefore better machines the microstructure of the sample we are hitting with LSP. Our experimental setup consisted of an NDYG 1064 nanometer laser and directed at a nitinol sample suspended in water. We additionally placed two neodymium solid state magnets on either side of the nitinol sample to create a transverse magnetic field of 400 milliteslas. By removing these magnets, we could remove the magnetic field, and placing them back in, we create the magnetic field for both experiments. We used a variety of laser power ranging from 530 milliwatts all the way up to 2030 milliwatts to determine the optimal power output for the laser for LSP. We conducted the analysis of the samples we hit, the nitinol samples we hit, using optical microscopy. We have some pictures here from the optical microscopy. As you can see, at 530 milliwatts with no magnetic field present at 10 shots, the crater size is quite large. However, when the magnetic field is placed, when the sample is placed in the presence of the magnetic field, the crater size decreases substantially. Additionally, the surface of the sample is more uniformly machined. The same trend is seen in other power levels at 230 milliwatts and also at 2000 milliwatts. As you can see, the crater size is quite larger here and decreases in the presence of the magnetic field. The same is seen for other types of samples of nitinol. In conclusion, the results indicate the effectiveness of laser shock peening in machining the surface of nitinol. As you can see, the magnetic field decreases both the crater size and more thoroughly and uniformly machines the surface of the nitinol sample. These are key features of LSP improving the fatigue resistance of the sample. Our next steps in our research are to perform X-ray powder diffraction of the samples, SEM, and material property analysis of the treated samples to determine whether LSP does indeed improve the fatigue resistance of nitinol. Thank you very much. I hope you found this informative, and please feel free to ask me any questions if you have any.